Hello, and thank you for joining me. Today I'll be going over the Kollmorgen AKD Basic drive. I'll be giving some examples of what it looks like to start a program, and also going over some of the features that Kollmorgen has included on the AKD Workbench software to make it easy to use the basic drive. My name is Kevin Young. I am the Indiana Motion Specialist. I've been with C&E Sales for over 10 years. And what you see in the image below is a group of individuals who maybe you've worked with, those of you familiar with C&E Sales. This represents our engineering support staff covering our PLC and automation line, control line, safety, and vision, and also motion. Anytime our customers are working on a project and they could use some assistance on picking out the correct hardware or software solutions, we often get involved with the salesman to help come up with a bill of material that meets your needs for exactly what you're working on. And as many of you know, we also show up to help out with your on-site startup. So maybe there's some faces there you recognize. To really give an overview of the AKD Basic, I thought I'd start out with an example of, or at least my opinion, of when I would use the programmable drive, any programmable drive really, or in contrast when I would not use a programmable drive. I would use a freely programmable drive in applications where your motion index needs additional decision-making capabilities during the move. So a good example of this is when you told a servo motor to move to a particular position, but during that traverse, you're monitoring the motor torque, for example, and then you wanted to make a modification to the profile based on that torque. Let's say maybe you wanted to increase velocity or decrease velocity during the move. So that might be an example of monitoring real-time drive level data and then making decisions based on that. Typically, if you're adding a drive or multiple drives to a typical PLC, the PLC doesn't have the built-in ability to monitor all the drive parameters. So it might make sense on simple applications to add a programmable drive, let it do its own decision-making, and only report back to the PLC via inputs and outputs or on field bus that it has done what it was supposed to do, monitoring the variables that it was predefined to monitor itself. Where I would not recommend using a programmable drive would be on machines that have a high I/O count. Bottom line is there's just easier ways to do that utilizing a PLC or even a motion controller that has PLC capabilities, either ladder logic or structured text. And then the other thing I always think about is once a machine is in the field, who will be the individuals that need to go online with that and troubleshoot it when it's in the field if it's different from the person who programmed it. And oftentimes I'll lean more towards a ladder-based control system or a structured text even, but mainly ladder. So anybody who's familiar with that type of environment can go online with the device and help troubleshoot the machine in the field. So that's always a decision-making item that goes through my mind. An exception to this is possibly if you're an OEM or even an end user and you've got many drives to install and you do need this decision-making capability on board, and want to add a lot of PLC cost, and it's a scenario where the design of the program and the debug could take place on the first or second install. Everything gets squared away from that point on. It's just download the program into the next drive and do all your installs up to 20, 25 drives or more, whatever, but not necessarily expect to make changes on those drives in the field over the course of a year, to where you also have to go back in and do more troubleshooting, add inputs and things like that. To me, with a PLC doing the control, it's just easier to do that in that type of environment, ladder logic environment. However, there is substantial cost savings by using these AKD Basic drives. So if it is a repeat cookie cutter kind of thing, and many of them to install in the field. You can save a lot of money as long as you are familiar with the requirements for going online after the fact and doing your debug and who might be doing that in the field. There are two models of the AKD Basic drive. One is the base version with the standard I/O count of 8 inputs, 3 outputs. With that, you have 1 analog input and 1 analog output. There's also the expanded I/O version. It gives you 20 inputs, 13 outputs, and 2 analog inputs, 2 analog outputs. As a baseline comparison, on the 3 amp, 9 amp peak drive, if the base I/O count, it's around $950, and with expanded I/O, around $1,260, so $300 more, gives you higher I/O count. There are 122 40-volt versions, single-phase, or three-phase, and then there's also the 480-volt version, three-phase, available. So this is where I would typically get involved and work through a model of your application, what mechanics you plan to use, what your load is, and what your motion profiles look like, and then come back to you with a recommendation on which drive makes the most sense based on the motor that we're going to use and the current requirements. It's typical that you would be the one telling me what voltage you want to use, and then from that selection, then I'd recommend the drive. So as you can see, we have AKD drives up to 16 kilowatt. Free is always good, and the software, Kollmorgen Workbench, used to program the AKD Basic is the same free software that's also used to program their indexing drive and also just their analog drives. Workbench is used for all the AKD drives. You'll notice the text in this download area that is available at Kollmorgen.com. Specifically says Workbench graphical user interface full setup. It's jumped over to AKD Basic servo drive Workbench. Uses the term AKD Basic. If I didn't drill down to the information under the Basic drive on the website, but I chose the positioning drive, the wording here is a little different, but it is the exact same file. So if you have not installed Workbench before, you do the full install, or if you're just doing an upgrade on the version, there's a smaller file to do the upgrade. Another file that can be downloaded and is of great importance here at the Kollmorgen.com website is the AKD Basic sample programs. And this is a compressed file of many programs. There's 14 in there right now. Not long ago, I think it was only about 6. So they're adding sample programs all the time. And the expectation is that you could decompress this file, open up one of these sample programs, paste it into your program environment, and use that as a base reference to start with. Also, something I do quite a bit is open up a program to check some format issues or things like that. And I'll go into a few more details on the available programs on a later slide. To make sure everyone understands what the programmable drive is, I've got a feeling that many people understand what an indexing drive is. So I'm going to set this indexing drive description up as a base to compare it to, and then dive in deeper about the AKD Basic drive. So there's a clear definition between, okay, what does a basic positioning drive do that you can program versus an indexer that you really fill in the blanks. And that is the biggest difference. As I show on the windows I have illustrated here, with an AKD Basic drive, with an AKD indexing drive, or really anybody's indexing drive that has a graphical user interface, a software package to help you configure the drive, you pretty much start with a configuration wizard. You start at the top, fill in the blanks, and by the time you get to the bottom of the wizard, you've got the drive set up and ready to go. I show a couple examples here of setting up your engineering units. So we're a lead screw system, and this is using the Kollmorgen Workbench software for the positioning drive, and you'll see similar windows for the AKD Basic drive, and I'll describe to you how there's a built-in advantage in using some of these simple graphical user screens and then importing the raw data later. And it's a pretty simple example, and I'll show you that here in a minute. So back to describing what you might expect with a indexing drive. So you've got graphical windows that open up, you fill in the blanks. There's a ball screw system. If you had a gear reducer, you've got some entries to put in what that ratio is. If it were a belt system, a different graphic shows up to help you understand what these units are that you're inputting. And you can choose turns or teeth. You go to turns, then you're going to be entering things such as pitch diameter or pulley diameter to come up with the circumference. And then below that, you'll notice you can pick what your units are going to be. So as a comparison, I've left units here as counts. So at this point, you're really talking encoder counts. And on a later screen, I'll show you where I'm using inches instead, as you might expect. Another example screen that would be available to you in setting up an indexing simple drive might be the screen to define your home routine. This example shows that it will find a home input switch and then continue to rotate to find the 0 mark on the encoder. This particular one found the home switch where the red line is and then backs up until it finds that single location on the encoder to indicate its reference mark. It's a very precise way to reference your machine. You'll notice it's, again, fill in the blanks with the speed, acceleration, deceleration, and what direction it's going to go. And as you would expect, there's a screen to define your inputs and outputs and what their functions should be. Notice for this example, I have input number 1, digital input number 1, trigger my start motion. The next 3 inputs are used, maybe you've heard of BCD. Those 3 inputs will be evaluated as a binary number, if you will. So when all 3 of those inputs are off, it equates to a 0. If it's 0, 0, 1, so only the third one is on, that equates to 1. 0, 1, 0 is 2. 0, 1, 1 is a 3. So it represents a binary number. That's used to select which move you want to do from your index table that I'll show next. And then the other input will start home and fault reset, things you might expect. And below that, you can assign your outputs. I've mentioned the index table. You'll notice the table has numbers down the left, and that is your index number. So that's your reference number, the index that you're going to tell it to run. The AKD positioning drive can have up to 128 predefined indexes. Quite honestly, typically 5 or 6 indexes is about all I ever see used. Beyond that, people tend to go to a more intelligent front end or an HMI front end to a PLC on the front end of the drive, talking to it directly. But back to the index table, if I were to click on one of the index numbers, another graphic screen opens up and I fill in the blanks. And then once I close that, though, then it populates these squares, or you can enter your information direct. But the only point I want to make here, it's almost like an Excel spreadsheet table, excuse me, to where you tell it the position you're going to go to, the velocity expected to run, acceleration units, deceleration units, type of profile, if it's trapezoid or sinusoidal possibly, type of move, absolute move, or possibly it's going to be a relative move. And then after the move is done, what do you want to do next? So in this case, it says don't do anything. So that would be index 0 going to location 0 because it's an absolute move. Index number 1 is an instruction to go to location 12 inches. So 12 inches out from 0 at that speed and those accelerations and decelerations. And again, it's an absolute move. The next index does something a little different. That's why I wanted to go over this in a little detail. If I would select index number 2 and give it the start motion bit, rising edge, it's going to go to absolute position 8 because I've defined it as absolute move. So it's going to go to location 8 at that speed and those accelerations and decelerations. But once it's there, I do have a 200 millisecond dwell program here that doesn't show up on the screen. But once it's there, it'll dwell the 200 milliseconds. And then index 2 triggers index 3. Index 3 triggers index 4. Index 4 triggers index 5. Index 5, once it gets to the end of that, then stops. And as I mentioned, I've got 200 millisecond dwell time in between each one of those. So by setting up my select bits to indicate value 2 and triggering the motion start input, I move to 8 inches, and then I do these quick little 1-inch increments afterwards. So with 1 setup and start div, I've got 4 indexes. So that's very handy to use, and it's common to a lot of indexers to be able to do that. That's about all you should really be expecting an indexing drive to do. There are a few other things it can do, like programmable limit switch outputs, and I'm going to go into a little bit of detail on that because the basic drive can do that also. So that gives you a feel for, okay, now that's an indexing drive. Now let's compare the AKD basic programmable drive to this. So anybody who's familiar with basic programming would expect there's a particular program structure that you're going to utilize. Often it has variables defined up front, and then main program and subroutines below that. That should kind of feel comfortable. There is an additional section, and I'll go into a little detail here now. The parameters area. This is where you will find anything that is a drive configuration parameter that you would typically initialize the drive with these variables. Maybe it's your mechanical scaling, maximum current that you ever want to go to the motor, maximum speed, your acceleration, deceleration units that you want to use globally. You can change things dynamically later. But all your initial drive parameter configuration. So again, drive-related information. I'll go into a little more detail about this. So you've got your drive parameters area. Then you've got your global variables definition area. So I show a few examples here. Actually, on another screen, I go into a little more detail on that. Then you've got your main program area, subroutines area, and your interrupt subroutines. So with the AKD basic drive, with the base input level, out of the 8 inputs, you can have 7 of those assigned as interrupts. And on the expanded I/O, you can have 14 interrupts. Everybody who does basic programming usually wants to understand what types of variables can you use, what can they be defined as. So with the AKD basic, your variables can be defined as integer, floating point, non-volatile, string, and constant. And then I show some examples over here to give you a comfort level of what that might look like. So I've got a variable called pointer, dimensioned as an integer. I can define multiple variables on one line to save space and keystrokes. So you see I've got L1, L2, and L3 all defined as integer. I've got color defined as a string, 16 characters long. Default would be 32 if I didn't have anything there. And I believe it goes up to 80 characters maximum length. The next line I have an array defined. So a variable called set A is defined as an array 2 by 5. So that would be 2 columns wide, 4 rows tall, 2 by 5 array. Then the next 2 parameters, diameter I've got defined as floating point, circumference as floating point, and then you can have constants as well. So if you're going to use pi and you don't want to put in the wrong number, I've got pi defined as 3.14 on out. So anytime I use pi, it'll use that number. And then you can also have constants as strings. And here's an example if I chose greeting 1 or greeting 2, maybe it speaks different languages. I ran a little program just to prove that, yep, my definitions work. So as an input, I input a string color. I typed in purple, entered the diameter, floating point 1.7. Then I had the program calculate circumference using pi, and then I show that it can spit the text back out to me that was defined as a string, and the results of the calculation. At a glance, most programmers have certain functionality they expect their basic programs to include. This is just some of the functionality that the AKD Basic offers, but if you have your favorites, you can look down through the list and pull those out. I know I'm normally looking for sine, cosine, tangent, and with those I can get a lot done, you might say. And then as far as the operators, the Boolean operators, you can see you've got your typical and, or, exclusive or, and then some binary things also. So the typical design areas, as you would expect, you can have multiple programs open, and it's very common in this environment to have your favorite programs, if you will, or ones that you've used in the past and they work, and go and pull sections of that code, cut it, copy it, and paste it into your new code. therefore you're not writing program over again. And again, as I mentioned, you know it worked, so you want to grab it and use it again. So you can do copy and paste from there. And of course, I've mentioned those sample programs, so you can copy and paste from those also. So you can have multiples open at one time and edit as you wish. Taking a little bit of a step backwards, here's what it looks like to start from scratch. So I've opened up Workbench, and I haven't even told it what drive I want yet. I would start with insert a new drive. So this window would pop up, and I tell it I'm going to do some offline programming. It's an AKD drive, the basic, and then the size of the drive, using analog input, not necessarily using a field bus or anything. So those values are fill in the blank, and I say create. After about 10 seconds or so, now you get the screen that you see on the left has a tree for selection. Because it is an AKD basic drive, and FYI in the drive model part number, you see AKD and then T like text. That indicates the basic drive. If there were a P there, that would be for positioning drive. Depending on which drive you selected in the previous screen, the list on the left will look different. Very similar, but different. So the AKD basic drive will have the input where it shows program. It's got a little robot beside it, what that icon is. So it's got an entry called program. If this were the basic drive, it would not have that entry. But if I were to expand the settings, there would be a few more things it would have that the basic program drive would not have. So just case in point, if you get into setting up a drive and you don't see program, just remember that is a dynamic tree on the left, and it depends on if you pick the correct drive to have that capability or not. You cannot purchase a AKD basic drive and then say, oh, no, I just want that to be an indexer, and then change it to make it an indexer. They are different pieces of hardware with different firmware, very different firmware on them. So it is a different part of the number, a different purchase. So once we've got the basic drive defined, and I've double-clicked on the program, I have the option. It would have opened up just a blank screen, and then I have the option to start a new program with the icon that looks like a little plus on a page. So what I am showing here are two different options. One is just to do a basic program start. So it gives you a simple format, and it really doesn't fill anything in for you. It says totally white page, if you will. So I show what that looks like over to the right. Remember the parameters section where I said all the drive parameters would end up? Notice it's empty, and I'll go into a little bit more detail on that. You've got your global variables area, you got your main program area, and then areas for your subroutines, but nothing's there. I prefer to choose the next option, which is start a basic program using current drive parameters. So on the next screen, I've selected that choice. If you remember previously, I did define that I've got an AKD basic drive. So what it has done is it has populated the parameters area with every drive parameter. So 243 parameters in this example with all of their default values. So if you were to download this program into a drive that's been in the field or been used already, it would reset the drive back to factory defaults. Now, that's not as common as scenarios where you wanted to have the drive set up with very particular variables to start with. And there's an added feature with the AKD basic drive where you can still utilize the graphical user interface setup of the drive, and I'm going to show an example of this, and then import those parameters the way they were configured. So you can use the easy-to-use graphical user screens to set up some of your parameters and then pull them in. Now I'll show an example of that here next. So for the example, I'm going to set up my mechanical scaling units using the graphical user interface screens. And then I'm also going to set up a programmable limit switch. And most of you probably know that a programmable limit switch is an output from the drive that's going to turn on based on the position and then it would stay on typically until an off position. So you've got a turn on point and a turn off point. The wording that they use with the AKD Basic, and even the positioning drive uses the same approach, is it asks for a turn on point and then it asks for an on width. So if I wanted this actuator to move out to 8 inches and I wanted the drive to turn on an output at 8 inches, and then anytime that actuator was sitting there between 8 and 10 inches, so I want a width of 2 inches. So that's the example I'm going to go through. So to configure the units, I've expanded the settings tree on the left, and now all these graphical user screen choices show up that I can choose from. So I've double-clicked on units. I'm going to use that screen to set up my ball screw system. It's an 8 turn per inch ball screw, so I enter my lead as 0.125 inches. And in this example, I've got a 2-to-1 gear reducer, so 2 revs of the motor equals 1 revolution of the output shaft. So in essence, with an 8 turns per inch ball screw and a 2-to-1 gear reducer, 16 turns of the motor is going to equal 1 inch of travel. Now, I don't want to talk about turns when I go to program things. I want to talk to it in inches. So I can have some more setup choices down below. My position units will be custom, mechanics dependent. Velocity units will be mechanics dependent. Same thing with acceleration units. And then here's where I picked my units to be inches. Could have been millimeters, could have been centimeters. But in this example, I'm using inches. So now when I tell it to go to a position, if I enter 8 and tell it to go, it's going to equate that to 8 inches. And that would be 16 revolutions of the motor. It takes care of that for you. I mentioned I was going to set up the programmable limit switch as well. I prefer to do this using the graphical user interface instead of going to each parameter one by one and entering the data. I'm just more of a graphical person who like doing it this way, and I know that my program can just pull in my configuration for me in the next step. So I've gone down the list. Here's where I used to be at units, so now I've gone on down to my programmable limit switch configuration. Open that up. Put a check mark to enable one programmable limit switch. It's going to be continuous mode, so it'll work backwards or forwards, not just a one-shot. My on position I show for 8 inches, as I said I would. Units, I'm using position. Just a point to make with the AKD drive, you could define this as a time pulse or position units. A time pulse, once you went past that position 8 inches, then that output would be on for a predefined duration in time. Let's say you want that pulse to always be 500 milliseconds no matter how far you were going, and even if you stopped in between 8 and 10 inches, for example. But in my example, I'm using position, so that's the units, and the width of my on period is 2 inches after the 8-inch turn-on point, so that's 8 plus 2, so anytime it's in between 8 and 10 inches, that output should be on. Down below, I assign that to my output with a check mark. So now I've assigned programmable limit switch 1 to digital output 1. So I did all that with graphical user interface because I think it's easier. Now, if I start my basic program and I choose start my basic program using current drive parameters, it's going to pull in any parameter that was predefined in the drive. And just to prove to you, if you will, the parameters that were specific to turning on the PLS output. Here's the PLS enabled. It set it to a 1 for me. PLS mode, as I mentioned, was going to be continuous. The on position was 8 for 8 inches. Down below is units. We're going to use inches and not time. The width was 2 inches. So there's all that same information put into my code for me. And then over here to the left, again, you can see that that parameter section is my whole data set of drive parameters. And included in it, here, the example on the right, I showed those line numbers where the PLS information showed up. So to me, this is a really easy way to do that kind of a setup. Another classic example is if you were to do your servo tuning and use the graphical user interface for servo tuning, save your parameters on the drive, jump into your basic program, and pull those parameters in. Now, maybe it's jumping into your mind right now, what if something changed? Or let's say I already had my program written, and then I wanted to go do my configuration. I don't want to start with an empty screen and have to cut and paste. you don't need to. There's an additional icon. I've got my mouse over it now. It looks like a little piece of paper with a pencil on it. If you click on that, if you hover over it, it says Edit Drive Parameters. If you click on it, then it tells you, okay, I'm going to import all the drive parameters and overwrite what's in your program. It's the only choice, but it's the right choice. It just brings in everything. So any changes you make, you can just go back, click that, and it'll bring in all your new parameters and put it in your basic program for you. I mentioned the sample programs. So here is that zip file decompressed, just to show the names of the files. To give you an idea of the examples that they give you, there's two different CAM examples because you can do canning and gearing. One, this is an AKD Basic drive. Well, Basic doesn't mean it's a low-end can't do anything drive. It just means it's basic programming. This is an example of a CAM profile. By entering your data points and some defining factors to smooth the transition and make it look like a sine wave, it will do calculations for you and create the sine wave. This one happens to be a 500-point CAM table that the slave drive would follow. So that's a more detailed example of a CAM profile. There's a simple CAM table. This one only uses 5 points, for example. There's a demo program for a relative move, demo program for a velocity move. Example using some math, gearing, various types of homing, home to a hard stop, home to an input, home to a mechanical zero. There's a Modbus instruction example. There's PLS, use of PLS outputs to trigger various digital torque commands. Then PLS interrupts. This one uses positions to set different currents as well. So this compressed file that you go and download will grow over time. They'll keep adding more and more sample programs to that. And if you're like me, you like to either go look at a sample program that checks and format examples, or even if it's really close to what you're going to be doing, start with that sample program, put it into your code, and go from there. Another way that Kollmorgen makes it easy to use the AKD Basic drive is what they call code snippets. There is an icon on the top of the configuration window, so I've got my mouse over it now, and if you click on that, it opens up this code snippet window. And what a snippet is, maybe you can pick up by the example names that are there, is a little section of code that you might use over and over. So they give you this ability to select it and drop it into your code. So you put your mouse wherever you want to add the code into your basic program. You pick which one of these you want to use. Not only does it drop it into your code for you, just before that, it's like a mini wizard, if you will, that you fill in the blanks. So in this example, I've selected an absolute move code snippet. This window opens up. I can enter my acceleration rate, decel rate, my speed, and my target position. So I told it it's going to be an absolute move to target position 1 inch. It gives you an example of what your code is going to look like before it puts it in your code. And then if you click on OK, it drops that in your code for you. Notice it also includes some text, text description to go along with the code that it dropped in. Of course, you can go in and manipulate that, change the text if you like, but it's handy that it throws that in there for you. Once you've got your program configured and running, and there is an editor, and if there's any edit errors or format errors, it gives you the typical, there's a disagreement on line number such and such, and it gives you a comment on what it thinks the problem is. For example, it might have said, expect a then at this location, or expected a colon at this location, so it gives you that kind of feedback. So let's say we're beyond that, and you've got your program up and running. You might ask yourself, what type of real-time debug tools are available to AKD Basic? So you have a watch table, what I might call a non-intrusive ability to watch your program. So you can pick a variable, add it to a watch table. enable it with a check mark, and then while your program is running, you can watch your variables real time as your program is running. As you can see in this example, it was running 2350 RPM, digital input was on, and you can see current command and current feedback. So it was flying at 2300 RPM and not using much current at all. Also handy, of course, in larger programs is the find or find and replace. So that's available as you might expect. A little more intrusive debug tool are the option to put in breakpoints. So there's F keys, F9, F5, for example, that will manipulate these, or you can choose from the debug menu and insert breakpoints wherever your mouse is. And I put one in. I could have had 3 in a row here. You put in as many as you want. But I show one breakpoint in my code. When your code is running, you'll have this kind of bluish background to it, so you know it's running. I put my breakpoint in, so only when the interrupt is triggered, this interrupt happens to trigger off of input number 2 going high, only when that input is triggered would it go to that portion of code, and when it does, I'll get this breakpoint, so the code will get to that point and pause. So in my example below, this is what it looks like when it has hit the breakpoint, and it says, okay, I'm at this point right now, and I have paused, and it's up to you to tell it what to do next. If you notice, I can click on the next icon, or I could have used the quick key F5, and it just would have gone to the next instruction. If I had multiple breakpoints in a row, it would pause at each one, and I could hit F5, F5, F5. And that gives you the ability to freeze your program, take a look at your data, and then go on and help you debug. I already mentioned the AKD Basic can do camming and gearing. I thought I'd give you a quick look at maybe what that looks like. This is from the sample program. So if you would open up the sample program and drop that into your program, it's going to guide you somewhat through their example on the number of points they used and the constants they used to generate their sine wave, and it gives you a starting point, if you will. And then I also show a gear ratio just so you get a feel for what some of the what some of the parameters look like that you might be dealing with respect to putting in a gear ratio. And I want to leave a little bit of time for questions, but before I jump out and look for questions, I also wanted to point out, of course, that we have all the mechanical actuators and gear reducers and things that you might expect would go with a servo motor application. Of course, we also have stepper drives and variable frequency drives. Anything to do with motion, I would be involved with. So feel free to call us up or call your local rep and get in touch with one of the motion specialists. Some things that maybe you haven't seen out on the market, in the upper left corner, that's profile rail with built-on rack segments. So with that assembly, you're installing one rail that already has the rack, so it's not 2 items that you normally have to install. Quite often you have 2 parallel rails plus the rack, so it's 3 items total. Now you cut it down to 2. These are very precision installation items, though, so being one more item out of the equation really speeds up the assembly time. So if you envision that rack system, and then we have pinions that mount directly on the face of the gear reducer, which will mount right on the face of the motor. And then we have heavy-duty systems available that also include an outbound bearing system to be able to give you some really high thrust capabilities. But maybe something you hadn't seen before on the market. Probably quite familiar with gear reducers, rod-style actuators, and ball screw actuators or belt actuators with built-on profile rails shown on those. So with that, I'm going to pay attention over here to the questions section. I haven't seen it come up yet. Let me go ahead and expand that. So that really wraps it up for my presentation. Appreciate, oops, I lost my mouse. Appreciate you guys joining us today. And any questions you might have, feel free to call the senior office. You can ask for Kevin Young. They'll tell you how to get a hold of me. My cell phone is 317-989-7733, and our website is shown there as well. We'll take a look here at the questions. I'm not seeing any open up. I'll keep watching, but thank you very much for joining me today.